Thank you very much, Diana, for organizing this meetup. It's very nice to have the opportunity to be here and see a beautiful city and people interested in big data. So I'm from the Bay Area in the US. I work for a company that is called DataTorrent, which was founded in 2012. I'm co-founder of the company. And we basically we wanted to build a stream processing framework on top of Hadoop Yarn. About myself, when I speak English, you will know that I'm from Germany, and when I speak German, you will know that I'm from Saxony. So I have been living in the US for since 2000 though, so it has been quite a while, and I always love to come back here and enjoy my vacation time in Germany. So DataTorrent is the company behind Apex. Apex was open sourced in August last year, actually. So it was developed as proprietary software for more than 3 years, and then became open source. This is a general trend that nowadays people want to see the bits in open source, right? And so we went to the incubator August last year, and it became a top-level project in April this year. So not too long ago, we are busy building community by doing talks like this, attending at conferences, writing blogs, and so on. We basically want to spread the word and make people aware of Apex. Is an awesome piece of technology. Many things that you find in Apex were built there first. It's just that it was proprietary and nobody knew about, but now it's out there and we want to have people use it. So let's start off with a small survey here. Who has worked with a stream processing system so far? Okay, good. That's about 50%. And like Storm or Spark streaming, or what is it? Storm. Good. So there is some knowledge about true stream processing, because Spark streaming isn't stream processing, as I will allude to later, but Storm is. So what is it about? We have many data sources today, more and more data sources and higher volumes of data, and we want to do more with the data that we have. And that gives rise to the new processing frameworks, because things like MapReduce don't really fulfill the requirements that we have any longer. We cannot wait hours before we can compute a result. We cannot assume that inputs are finite and can be processed as a batch. So continuous events, as it happens outside wherever you look, right? It's a continuous stream of events. So the processing should be like this too. Examples here for the kind of data that you can get. And these are just some examples, but everybody is probably familiar with social media streams. They definitely don't stop. Then logs, web server logs, or any form of log files continuously being appended, and we may want to do analytics on it. So in a broader sense, events that continuously occur, we want to take them into the processing framework, do some computation on it, get some useful results. The aim is, of course, to produce results that give business insights. There needs to be some value. Why are we doing all of this? There needs to be a value proposition. As the data is getting older, the value of the data also drops. So typically, the more recent it is and we can gain an insight, the more valuable it will be for businesses. So you see that Apex sits here in the middle. It's a processing framework. It's not a data delivery framework. So the sources are here, possible data, possible delivery mechanisms, and these are just examples are here, but most prominent is Kafka. Probably all of you have heard about Kafka, and you know that more and more organizations use Kafka because it's a really good way to deliver data with low latency into a processing framework. It was created by LinkedIn, and they have built an entire architecture around Kafka, a decentralized, decoupled system out of many different components that can be independently maintained and upgraded. So The idea is that in Kafka you can have all the data and you can keep them there and you can always replay it, you can recompute, you can come up with a use case later that you haven't thought about originally, but you have the data and you can compute what you want from it. And the storage is, of course, files, and it's cheap, right? Compare that to a database which will burst at some point because of too much data in it. Files, commodity, hardware, HDFS or file systems on Kafka brokers, cheap. We can keep a lot of data. So Apex is a consumer of data that gets delivered. So here we want to model applications that have business logic, that do some meaningful processing, that give us results that we can act on. Apex runs on top of Hadoop, on all of the Hadoop distributions. It was built actually for Hadoop, for Yarn. In 2012, when the company was founded, Yarn came just out, Hadoop 2, and the first alpha version of Yarn. And we started to build what is today Apex on top of it. You can model applications as a directed acyclic graph. That concept might be familiar. You can arrange processing logic in sequence, in parallel, on a logical level, and you can express many different things that way, which you couldn't do with MapReduce because you only have map and reduce, and then that's all. And then you have to do more map and reduce and more map and reduce and stitch it somehow together. The frameworks that are out there today, and this is not just Apex, it's also Spark, it's Taze, and so on, they all have a more richer processing framework that lets you model actually things in a more natural way. So then what can we do with the results? We may want to land them in different destinations, very often in databases, because that's what people have, and this is what they know. This is also how they know to query the data. Everybody knows SQL, and then how to connect SQL to a database. That works well. So we might want to put the data into Oracle or into Hive, into MySQL, or in a different database, a NoSQL database, Cassandra, HBase, and so on. Again, these are just examples. But the point is, the entire picture is one of integration, right? You got the data, you got something that delivers data, you got something that processes data, you got a destination for the data that ultimately goes to the user or for further processing. So it's not just the stream processing engine, it's also the connectors and the integration pieces that matter a lot. And Apex has a pretty rich library of those connectors pre-built that you can already use. You don't have to build it yourself. So an interesting concept is also that data can be delivered directly from the stream processor for display by the user. So imagine you have a dashboard and you wanted to see the data that is computed right now. You don't want to wait until it's written to a database and then load it from there, because that can take time. In most cases, there's latency involved there, because you cannot really dump so much data into a database so quickly, or you have to batch it to make it possible. So there is this idea that you can actually deliver data as it is being computed to a visualization dashboard. So that's something that DataTorrent, this is a proprietary tool that's not part of Apex, that DataTorrent lets you do. Deliver data to dashboards from in-memory state of the application. So use cases. Many different verticals can benefit from a stream processing system. You will find various things here that require low latency processing, where we cut the weight. There are also use cases that require fault-tolerant processing. I will come to that, why it is important that you can actually maintain state in a stream processor. That is not lost when it is shut down or when it is restarted, because you can do a whole lot more than what you could in some of the older systems that cannot keep state. So financial services, imagine you have fraud detection. You have a credit card, you swipe it at a terminal. You have only very little time, right, to compute the response. Is this a good transaction or is this a bad transaction? You want to accept, approve it, or decline it? It's milliseconds, right? So a system needs to be able to do low latency processing. Now, this is an example where you really need very low latency and an SLA on it. So even when there's a failure, you cannot afford to have somebody wait, well, for a minute until everything is back up, if it comes back up. So another one that is sensitive to latency is advertising technology. The people that pay the money they want to know that their campaigns are doing well. They want to have some insight, whether it's worthwhile maybe to add more or to reduce the exposure and so on. So ad tech, there are many small companies that are doing real-time processing. I believe there are a bunch of systems out there that have been implemented with Storm. There is DataTorrent has a customer that has built something like this with Apex. Things like, okay, get me all the click data from the web server logs, do some computation on it, do some aggregation, tell me how many clicks for a given publisher or advertiser in the last hour or in the last day, and then derive some actionable insight from this. This is a case where you actually want to get the data fed into reporting back to the user. Telecom is another area. So you could imagine that when you have the wireless networks, that you want to know about capacity, potential bottlenecks, before the users notice it. So let's say you can continuously cover call data and you can find concentrations of users in a particular spot. It would be nice if you can adjust the capacity to satisfy the demand, but also to scale back the capacity once the demand is no longer needed. So imagine you have a Fußballspiel somewhere, and there will be a lot of people in one spot. You may need more. You may need more capacity temporarily, but you don't need it all the time because the rest of the time the stadium is empty. So there is a lot of analytics that can be done on call data too, and you can imagine that it plays also into online advertising. What if I want to offer somebody who is in a particular place based on the location data something that is being sold there? So the seller may want to know that somebody is there and make an offer. Then manufacturing. So one of our customers, a large company, General Electrics, probably you have heard about it, and they have machines everywhere, right? And now machines are being changed, that all the different parts in those industrial machines, they have sensors. What they want to do, they want to have predictive maintenance. That means we want to know beforehand when certain parts are at the end of their life cycle, need to be replaced, etc. It is much cheaper to detect such things before we have an outage, and it's also less, it's less costly. Right, so there's an example from the IoT space, industrial machines, and then energy is similar way. This is actually similar to telco, right? You have also demand and supply, and it's elastic and it's changing. So if you can tap into sensor readings, then you can do certain analytics, and you may find out that infrastructure needs to be expanded or changed, or you may find certain problems that otherwise would be hard to find. So an interesting example that I remember from a colleague of mine who had a Comcast is a large internet provider in the US, and they give the devices to the similar to probably what is happening here. They give a device which is installed on-prem, and then that's your box, right? And it delivers the internet to your house. So now sometimes these devices they go out of sync with their firmware. Sometimes the way the cabling was done is different between different areas or different houses, and at some point there are problems because things stop to work. So wouldn't it be nice if you have one customer who is affected by that, if you can find all the other customers also who have a similar problem? And that requires analytics on large amount of data. This is something that you can do if you continuously capture data and then run the analytics on it. It's obviously much nicer to call the customer or send somebody there and fix the problem before they even notice. So those are example use cases, verticals, but then also horizontal use cases. So Apex works also very well for bringing data into a Hadoop cluster. Let's say you have it in Kafka, you have it in files, or similar sources. You can use the Apex interconnectors to bring it in a fault-tolerant and reliable manner without losing data. Uptime is guaranteed. So ingestion is actually a good use case, but it's not specialized on ingestion. So it's not competing with things like Kafka or NiFi and Flume and other frameworks. Those are sources for Apex. And then we have things like data quality enforcement and data enrichment, pre-processing of data before we store it in the cluster, and so on. So bringing data into Hadoop clusters is a problem everyone has to solve before we can do any processing on it. So now Apache Apex, this was more general stream. What is stream processing and what are use cases for stream processing? Now we want to talk about specifically what value does Apex provide here. So it's an in-memory distributed processing system. That means we want to run logic on multiple nodes distributed in a Hadoop cluster, and we want to minimize the occasions where we have to move data over the network as much as possible. We definitely don't want to write it into files in every processing step like it would happen in a MapReduce job. We want to cut out that I/O. We can get higher throughput, lower latency, and overall better scalability. So application logic is being divided into what we call operators. Those are components that are like a function that encapsulates some business logic. Could be pre-built, could be custom. And then each of these operators, they get data one event at a time and compute results. Now, one event at a time is important. It's streaming first. That means we don't wait for an hour or for a few seconds and then give that for processing. That would be a batch framework, right? For example, Spark is a batch architecture. What we do instead is we take an event as it arrives and we pass it through a processing pipeline, like a car assembly pipeline, right? It goes through many stations. As soon as we have completed one station, it moves to the next one. There's no waiting for like 5 cars before we start working on something. So that's stream processing. One event at a time lets you do low latency processing, minimum waiting. Another important part here is to maintain the state of the system. So let's say we have one function that is counting. We just have a very basic example. Everybody understands that. We count the lines that we receive. So it's going to increase as the data arrives, but what happens if there is a failure? What happens to that count? So we don't want to lose it, right? Because we may be counting something important. So the ability to maintain the state by the platform and to restore it when there's a failure is important. That's something that Apex is doing. That's definitely something that the newer architectures can do that previous systems have not solved. If the system cannot maintain the state, then it gets very inefficient and there's a limit on how far you can scale that, because on every operation, if it's a stateless system, basically you have to swap the state to disk. You get the next piece of processing scheduled by a scheduler, and then you have to load the data back into memory just so that you can do something. So I have my count. Now this slice of processing in the batch processing system completes. Now I have to write it somewhere. I have to figure that out myself. Then and the next task comes up with the next batch of data. I have to bring it back into memory before I can resume the processing. That's inefficient, right? And it's very hard also to solve on user level code. This is much better left to an engine. And then finally, a third concept, event time processing, which actually is based on the ability to maintain state. So if it's a continuous flow of events, then where is the boundary at which we can compute results? There needs to be something, because otherwise we will never have a result. There's always more data arriving and we are waiting, no results. Well, we want results. So there's the concept of windowing in stream processing. We define a window, and that sets a time box over which we want to compute results. So again, we have to be able to maintain state, and then we have to at some point set that temporal boundary at which we can emit the result. And maybe after that we continue to aggregate, but we have a result, a partial result. There are different strategies. It can be, the state can be collapsed and given to the next processor, or it can be incremental. There are many different options in windowing, and we will cover that a little bit later. So the next item which I would suggest to pay attention to when looking at the stream processing platform is the scalability aspect. So is it really written in a way that lets you, where you can make good use of your hardware, and by adding more hardware you can process more data? So I will give you an example that is in conflict with horizontal scalability, that is Spark streaming. In Spark streaming, you have to schedule individual tasks. So in Spark streaming, those are very small, right? 500 milliseconds, 1 second. Okay, you almost don't notice it from the surface, but they are scheduled repeatedly. There's a busy scheduler who continuously schedules those RDDs. That scheduler is a scalability limit. There are only so many tasks that can be scheduled in a cluster in a given period of time. Contrast that to stream processing engines. They will schedule once at the beginning, and then the system will just keep on crunching data and processing without scheduling anything, because there is no need to schedule. It was already scheduled. We just want to process the data. There are exceptions. I mean, if the topology changes, if an error occurs, but those are exception handling. This is not like a routine scheduling that occurs. So the ability to scale and to achieve high throughput plus low latency, and the combination of those three things. Does the system provide you a trade-off with these three things that is acceptable to you for your use case and also for the future growth of data? So in Apex, you can scale operators up. You can have multiple partitions. It is efficient, so you can have high throughput. You can have low latency because it's a streaming first architecture, and the delivery of events between hops are efficient. There are optimizations also to avoid network hops and so on, which we can talk more later about. Then the next thing is the fault tolerance. So I had mentioned about the state. So if you track state, we have to make sure that the state is safe and is not lost under any circumstances. What can all happen? A process can die, somebody kill -9, a machine can be unplugged from the network, or it can have a disk crash. An entire data center could go offline too, theoretically, or somebody wants to update a Hadoop cluster, and then the application needs to be taken down and brought back up. So we want to have provision for all of these situations to bring the application back to its state with no loss of data, and also no loss of the in-flight data that have not been processed yet, because remember, data continuously arrives. It doesn't stop because our cluster has a problem. An interesting aspect of that is also that when we are talking about fault tolerance and processing guarantees, it's one thing to discuss it within a streaming engine. That means the streaming engine doesn't lose any data. That is fine. But as I said at the beginning, streaming engine integrates with other systems. It gets data from somewhere, it writes data somewhere else. So now you have to worry about the integrated systems. You do not want to duplicate the data in your Oracle database because the stream processor went down and got reset, etc. So there are then different responsibility in the integration layer to ensure what we call end-to-end exactly once. That means no matter what happens, the effects are not duplicated in external systems. And finally, operability. So the DataTorrent was founded by folks that have worked in Yahoo and have experience with Yahoo Finance, with running Hadoop clusters on large scale. And there were many lessons learned how important operability is. Because if you don't solve operability, confidence in the system is low. And some people will hate it because they will get paged at the most unfortunate times, and they will just waste their life babysitting things. It is very important that the framework also is designed with operability in mind. So the admin should be able to see what is happening. There should be tools to access logs. There should be automated recovery. When something goes down, it should be recovered without any human intervention, right? You don't want to be called in the night. The system should take care of it. And there should be ways to bring the system back up when you have a complete outage from a previous state. There are also a few extra things in Apex that are unique, such as the ability to make dynamic changes after the system is already running. You can make some configuration changes. You can even introduce new processing logic into the system after it's already started. And finally, the elasticity. That is also an interesting aspect. The utilization of an application fluctuates throughout the day. There are peak times and there are times when the system is hardly used. So it is often desirable to adjust the resource utilization to that. If we cannot do that, then it means we have to allocate the maximum, the worst case, and always hold on to those resources, but they could be used for other processing in the meantime. If I know that I have a peak at noon and the rest of the day things are pretty slow, then yeah, it would be nice if we can actually give back resources and allocate them when they are needed. So that's referred to as elasticity. Apex can do that. Apex is able to allocate resources from Yarn dynamically on the fly as it's running, and also give it back. And the triggering behavior when this event happens, when you want to scale up or scale down, that's actually something that is customizable by the user, because the framework cannot know that. You may look into your external, your message queue, your database. You may look at the directory, the number of files that are there pending for processing, and determine the resources that are needed. So again, this is something where the user has to have control and the ability to customize. So native Hadoop integration. Apex, or DataTorrent's framework, was designed to run natively on Yarn, which means that it can leverage the advantages that Yarn can provide. Those include security, multi-tenancy, isolation between processes. Yarn was designed, and actually there were several changes where Hadoop was changed for security, for multi-tenancy, actually with the realization that it is best to have a large cluster and share that between different groups, because you have a one-time cost of administration. There's one central ops team, and the utilization is typically larger when you have it shared versus you build many different island clusters. You have to maintain them separately. The owners are different. There's no central authority. So there are scheduling policies that can be configured in Yarn that determine how many resources one user can take. The applications always run under the user that launched it. So if I'm launching my application and then Joe launches another application, they will actually be isolated here. They will run under different users. They will obey different scheduling policies. They will play with security, and you have this effect of isolation. There are a few solutions out there that actually don't have isolation. They actually assume that there's a single cluster and it's treated like a shared resource where I can run anything regardless on what user submitted it, and then those processes, they can actually compete with each other for resources, even if that was not intended. In Yarn, you have an application master. The application master is the brain of the application. It has to figure out what to do, basically, to execute an application. The Apex application master has to look at the application that you have specified, take the logical plan, translate it into physical plan, figure out what the execution layer would be, then go to the resource manager, allocate the resources, and then deploy those containers. And then, so it has to take the operators and put them into the containers that it deploys. That's all the responsibility of Apex. That is not something that Hadoop provides. Hadoop provides the resource scheduler and the distributed file system underneath. And some of the things that I said, security, multi-tenancy. And in the Yarn cluster, how does it scale? You add more node managers, right? You can expand the cluster. You can add more machines, and then each machine has a node manager running on it. And this is how you can scale out. It's just important that the frameworks that are running on top of Yarn can actually take advantage of the scalability. So how do applications look like? In Apex, it's a directed acyclic graph. So you have operators that are connected through with these arrows. Those are streams. It's a graph. It's acyclic most of the time. There's one exception for iterative processing where actually the output of an operator can be the input of an upstream operator. But that's an exception. We don't have to discuss it here. The capability is there. Most of the time, it's acyclic. And the data is traveling through a stream, event by event, from one operator to another operator. You can arrange the operators in sequence, or you can arrange them in parallel, depending on what the business logic is that you want to build. So each operator can take one or multiple input streams, and it can emit one or multiple output streams. The programming language in Apex is Java, so everything is Java-based. When you write custom operators, you would do it in Java, except you write a script operator where you basically configure it with a script, but the normal way would be to write it in Java. It's more efficient. The skill set is widely available. The applications that assemble the operators into the directed acyclic graph, they can be written in Java. They can also be configured in a JSON format. And we are working on higher level API to simplify that too. So here's an example how such a simple application could look like. It's the hello world of big data processing, word count. So we get lines from an input file. We have to parse the lines, tokenize them, split into words, count the words, and finally emit the counts for each word. So you have that application pretty much in any framework. You can run it and you get word counts. So in Apex, it could look like this. You have operators that are pre-existing that you can use, line readers or file line readers, parsers, unique counters, and console output in this simple example. Those are operators that are in the library that you can use to build your application. This would be the piece of code that you write when you use the compositional DAG API in Apex. We are working on, or we have already the first iteration of a higher level API that is declarative. So this may look more familiar to some of you that have worked with Spark or even with Flink. It's a fluent API, basically where you can chain multiple things together. You can see that the same logic this is much more concise than this would be. Now, that's for the word count example. In other applications that may not look like this because you may actually require the higher degree of flexibility of writing an application. But there is not a single answer what API is the right one. We supply multiple and then user gets to choose. So I talked about windowing, and this is how the support for windowing that we are adding, which will very much look like what is in Apache Beam. So Apache Beam is Google's cloud data flow model that they bring to the Apache Software Foundation, which is an API that is open source, and there are multiple runner implementations. That requires from years of experience with many different processing pipelines how windowing semantics can be defined through an API. It's not easy, but I guess it covers many of the things that an engine should support to give the user the required degree of flexibility. So this here is an example how you could, with the Fluent API, define a windowing. So this would say we only have a global window. A different window could be a time-bound window, a window of 1 second, fixed window, right? Or a session window that demarcates the span between two different events with a timeout. So all of these things can be defined here, and then also triggers define when results are emitted. So we say, for example, after 1 second, we want to emit the results that we have accumulated to this point. So this is how you would add windowing to your application. And then finally, although there is a fairly comprehensive library of operators in Apex, it is not possible to cover all the needs of business logic that folks have, because the business logic is specific to one organization and not generic. So in our library, we have connectors and we have few generic operators like parsers that understand standard file formats, can do filtering, enrichment. So this here is how it would look like when we wrote our own splitter, right? There's a port receives data, in this case it's a string, which represents the line, and then the Java code is to split the line and emit the words in a loop. And the unique counter that you see below here, this is an example where you have state, because we don't emit anything right away. What we do is we accumulate state first, and that means that this map that contains state, the words and the count, needs to be saved. The framework has to maintain it. If anything happens, the operator fails, process fails, it has to restore that. Cannot lose the data. And then the state is updated on every tuple, and on a callback, the results will be emitted. And this could go to the next operator for further processing, which could be again a windowed operation or what have you. So the operator library, these are some of the things that we cover. It's a pretty comprehensive library that covers many of the integrations for existing popular Apache projects. So you can see things like Kafka, Flume, Kinesis for the messaging side of things. Then several NoSQL adapters that are written there. Those you can use, you don't have to write them. So some of the heavy lifting is taken care of to make them fault tolerant, to not write duplicate data, transactions, and so on. Then, of course, JDBC-based or SQL-based systems, Hive, S3, parsers with some of the standard formats, transform operators, and so on. So those things are part of the library that comes with Apex. It's certified with the Apex releases. It's not third party, it comes with the release and is first-class citizen of the project. So the stateful processing is an important piece to understand in stream processing. So here I have made an example, and you can see those are this here on the top above the arrow. That's the order of arrival of events in the system. So you can see this is the first event that arrives first is being processed first. Then next one, this is processed, and these almost arrive at the same time. Maybe I should have changed this a little bit so that it clearly says which one is first. But what you can see here, there's a timestamp, right? And this denotes that the processing order is not necessarily the order in which events were created at the source. So imagine you have a train running, and the train accumulates data as it's running. When it comes into the train station, it gets hooked to some terminal, and all the data is downloaded, and it goes for processing in the analytics system. What we care about most of the time is the time at which an event was created, not the time at which it was processed. So important capability, no matter in which order the events are presented to the system, we want to be able to compute the results that is consistent with the event time. It's called event time. So you can see here that we are doing some time bucketing, and we have the key as the timestamp hour 4, and it's 1 now, right? And then we have hour 5 added over here, and we have 2 events. And then we have another one with hour 4, and that's allocated here. So as the events are being processed, this state here is changing. And now it becomes clear that it is important that the state is managed properly. We can't lose it. We cannot add something to an existing state when this event arrives if this could be lost. So it won't be lost. It will be checkpointed in Apex, and it will be recovered when we have a failure. So the state management is important. The other thing that is interesting here is this sequence of events. I could replay it. If it comes from a Kafka topic, then Kafka would guarantee me always the same sequence, but not necessarily ordered by timestamp. But I could go back tomorrow and start from the same offset and replay the same events. So what I would expect is to get the same results, right? Because after all, I'm feeding the same data in, so I'm expecting the same result. And one application could be there's a bug in the system, and I just have to recompute the state because the bug got fixed, and I want the system to reflect this. If the system would just take the system clock to do the aggregation, this wouldn't work. It would suddenly get totally different results. A system that is doing that is Spark. It does not support event time processing. And it has the limitation of the state management, where actually the user has to write state saving, and state loading between tasks. So stateful processing, Apex can do it, Flink can do it, Beam defines it in the model. That's, in my opinion, true stream processing. So checkpointing. We said we can't lose the state. What do we do with the state? We need to save it somewhere. So in Apex, how that works is we have the stream of data that's here. The first event that got processed is here. The last event in this case is here. These light gray circles, these are the actual data events. So those could be the timestamp tuples that we are processing. The colored markers are control tuples. They are inserted by the engine at the source, and then they traverse the entire DAG. So what we get from that is that because they're inserted at every source, they will go through the entire topology. The topology is distributed on different machines, but the data flows through it. Every operator will get the same control tuples, Because of that, we can actually use the control tuple to identify when we want to checkpoint. And later on, we can go and tell all of these operators, hey, there was a failure, we have to reset. So you're going to restart from this checkpoint here. And then they will exactly know which state to load, each of them, even though it's decentralized and it's all asynchronous and there's no central authority managing this. Yes? Yes. Yes, I mean this is a system level concept here. This begin window, end window, these callbacks or callbacks that you get on your operator, you can use them. The windowing concept that I showed earlier, this is actually something that is on top of it. So yes, the state of the window is being saved. So let's say we counted to 5. The state is being saved at a checkpoint. Now it's going to continue. It count more. It will then save it again here. And in the meantime, it could have been updated. I will come to that. I have an example for that, but that's correct. Yes, it will not be repeated. The whole reason to have a checkpoint is that I have some state materialized, and it gives me a recovery point from which I can reprocess. Because we can't go back, data continuously arrives, so there's nothing to go back to. That's right, yes. So fault tolerance, how is it done? The operator state is checkpointed. We talked about it. It's checkpointed to a persistent store. By default, it's HDFS. And that's the default implementation. So Apex doesn't need anything but the yarn and the HDFS cluster out of the box. The handler, though, is pluggable. So you could implement your own destination to store the data. For example, to store it into an in-memory data grid or somewhere else. There is an example of that in the library for Geode, Apache Geode, which is the open-sourced version of Gemfile. So in-memory data grid, right? If you have a different system and you want to use it, you can do so. It's just the default out of the box is HDFS because it's available everywhere. It's automatically performed by the engine. There is no code that the user has to write for checkpointing. So you have your member variable. I'll show it here. You declare this, and unless it's marked transient, then this state will be automatically extracted by the framework and saved into a checkpoint. So in the case of a failure, operators are restarted from the checkpointed state. I have an example for that. The failures are automatically detected by the framework, either by Yarn or by Apex, and then the recovery is initiated. So Apex finds out that which operators are affected in that processing graph and then restores those. It can actually do incremental recovery. That means there's no need to reset the entire topology. It will identify which of the compute units are affected. So it's the compute unit that fails, and everything that is a downstream dependency has to be brought back to a consistent state and is subject to reprocessing from the checkpointed state. The rest of the topology can continue processing. It won't be affected. We have buffering that enables the replay of data. So when we have a checkpoint, then data in the meantime is accumulating still, right? And then when the checkpointed state is restored, then we have to apply everything on top of it that wasn't materialized in the checkpoint. So that's what the buffer is there for. Every operator has a buffer for the data it produces that can be given to the next operator. And then finally, the application master state also needs to be checkpointed because the application master holds the knowledge of what the processing topology was, on which machines the containers were allocated. When that process fails, which is a rare occasion, hopefully, then it has to bring it back. I said that we support dynamic changes, so if you can change configuration dynamically, if there is elasticity where the partition count changes dynamically, then we need to be able to restore that in the application master that monitors the entire DAG execution. It monitors it, it's not involved in the data flow itself. The data always flows between the operators in a decentralized way. So this buffer server, a little bit more detail on that. So you think of it as, so here's the operator 1 that produces some data. It gives it to that buffer server, which is part of the same process. And then there's a consumer for the data, which is in a different process, and in this case on a different node. So this is an in-memory PubSub, similar to Kafka without disk. Right? So you have a subscriber that says, I want to start consuming from a particular point, and you have a publisher that continuously pushes data into the buffer. They can also temporarily or for a longer period of time operate at different speeds, in which case the buffer server will limit the speed at which data can be produced, because there's a memory limit on it, and it can also spool to disk, but there can only be so much data produced as can be absorbed in a time interval. So on recovery, let's say this fails here, it can go back and resubscribe to a particular point and fetch all the data and apply it on top of the state, which I have here. So the simple count example, you have a sum, which it starts at 0, and this is our stream of events. Begin window, then we get 1, 2, and 4. We want to sum that up, end window. So after one window is processed, we have 7, and the next window starts. So now next window gets consumed, the first event gets consumed, we have 10, it crashes, and the state is gone. This is what was checkpointed before. So what the engine will do now, it will bring back the operator on a different machine, possibly replace the container, the yarn resource, and it will restore the state that was checkpointed. So this state is being loaded back into memory, so the counter will be initialized with 7. Now, what we have to do, because this was a partial window, but the checkpoint was really here, we rewind the stream, it will subscribe exactly here, and then it will again process 3 and then 1 and so on. And so you basically have a state and the ability to reapply data that has not been applied in the event of a failure, and you get a consistent result and exactly once within the stream processor. So processing guarantees, that's an area that is sometimes subject to confusion because different people use different terminologies. So let's discuss what we mean in Apex. So at least once means we don't lose any data, but data can be processed multiple times. So if there is no guarantee on the order of the events, that means when we replay, they are replayed suddenly in the, they are suddenly replayed in a different order, like suddenly the 3 would be over here. Well, that would be trouble, right? Because now the data consistency is all lost. So what is happening instead is in Apex we have exactly once. So we take the state that was snapshotted, we can guarantee idempotency on a replay, and so we can arrive at the same final state. Now, exactly once also means, I said that before, taking into account any mechanisms in an external system. If you write the database, we need to use what is applicable there. And for the database, it would be transactions. For file system, maybe we do atomic file operation to ensure that we don't have any duplication. So at least once isn't really sufficient. It's necessary inside the system. Idempotency is also needed to arrive at a consistent state, and exactly once semantics. When we talk to external systems, we need the mechanism applicable to that system to ensure consistent state. At most once is, there are probably not many use cases where we can do it at most once, because in at most once we say that we can lose some data, it's okay, but maybe we just want to process the latest. So there may be some applications, but typically that's not. Typically what we want is this here. So the end-to-end exactly once, to recap that, is important when writing to external system. Data should not be duplicated or lost. And here are some examples. Databases, files, message queues. Each of those has a different way of ensuring the exactly once semantic, and it's implemented in the connector that talks to the system, because only that component has the knowledge on how we can give that guarantee. So nobody can say that a stream processor can do end-to-end exactly once just by itself. That only works in conjunction with the external system. So, and then we have what we have, at least once, plus item potency, plus the consistent state, and we get exactly once. So scalability. Let me check actually the time. Okay, good. So scalability, there we have partitioning. The first part, that's pretty standard. So we have logical operators that are part of the application specification. And then we want multiple partitions for a given operator. So this is a way to divide the stream into multiple portions that are processed independently and distributed. So we can handle more data because we split it over multiple processors. When we split it, we need a way to bring it back together. That in Apex, that is called a unifier. It kind of resembles what you would do in a combiner or in a reducer. It understands, based on the computation that was done here, what the correct way is of combining the results into one. So that would be different when we do counting. Counting is just taking the partial counts and adding them all up. But if you do a top 10 compute, then we would have a different logic in here compared to the count. And finally, the last operator can then take the unified result and process that. On the right side, this here is shuffle. That means the data that is result of the first partitioning is shuffled so that it can be fed into the next partitioning. The parallelism can be different between the two operators, and the subset of the data needs to be channeled to each operator, which requires to move the data over the network. So that's what all systems implement. An advanced way of doing partitioning in Apex is parallel partition. So again, we have our logical specification. It gets translated into a physical plan. Let's say we have two operators and we want two operators for each compute unit. So what we can do here is, instead of shuffling the result, we can actually say we don't want shuffle. We want the partition to continue. We want to chain it. And then we want the shuffle to occur later. So with that, we can do more efficient processing, because we don't have to move the data over the network here and not here. We do it only here. Another interesting aspect of that is, if we take this out of the picture, the fourth operator, then actually there's no connection between those parallel pipes. And so they can process independently. And if you have a failure in one of the pipes, the other one can still compute and deliver the result. Because Apex supports incremental recovery, that can be used to implement an SLA guarantee. Another piece is cascading unifiers. So here we could hit a bottleneck when we get a lot of data into a single unifier. And if the unifier is doing an aggregating operation, that means the result will be less in terms of amount of data than what the input is. Then we can actually avoid this bottleneck by doing partial aggregation here and here, by limiting the streams that go in and then repeating the operation in a cascading way. That is a very neat feature also. And finally, dynamic partitioning refers to the ability to change the number of partitions at runtime. So let's say we start with 2. Now, based on some criteria, we want it to become 4. And then maybe we want to also scale out another operator here in this example. So this can change while the application is running without taking it down and changing configuration and starting it again. We can implement a trigger that can look at various statistics and make a partitioning decision dynamically. So for example, Kafka cluster, let's say new partitions have been added to a Kafka cluster. We would like the Apex connector to automatically detect those partitions and process the data from those as well. That is an example. Or we do file ingestion. We have a lot of files in a directory, and sometimes we don't have no files. We want to scale the resources up and down that are allocated to this file reading. So then dynamic partitioning, how does it work? This is detail. I mean, we'll not say a whole lot about it here. The partitioning decision can be customized by the user. It's Java code that the user can write. The user can use any data that's available externally or within the system to trigger partitioning. It can be externally driven. For example, in the Kafka operator would be externally driven because we actually changed the partitioning in Kafka. It is stateful. So when we partition, we have multiple partitions and each of them has a state. So here, right? So now we had two partitions. Each of them, let's say they count. Each of them has a count. So now what do we do here? When we go from 2 to 4 partitions, we have to redistribute that state. It works in conjunction with the checkpointing. So the partitioning code has access to the frozen checkpointed state. It can extract the data from there and can redistribute it over the new partitions. So out of 2 checkpoint points or 2 checkpointed states, we will create 4 and bring up the partitions with those. It's the same mechanism underneath the covers. So it's stateful. And then what happens inside the engine when this happens, so the partitioner will be called. He will say, okay, I want to partition. The physical plan will be modified. The checkpoints will be rewritten, as I said. And then the engine will find out which operators are affected by that operation. They need to be taken down. Possibly resources need to be acquired from Yarn and then redeployed. And the system is back up and running with new capacity. Another interesting feature is compute locality. How can I control how operators are arranged relative to each other? So let's say what I want to express is I would like that this operator and this operator actually run in the same container because I know something about it. For example, I'm reading data from Kafka and the first operation I have to do is decompress the data. So now I have 2 operations. One is just waiting for I/O most of the time. The other one is CPU heavy and does the decompress. Those are friends, they can live in the same process. So there's no need to move the data over the network. So I can say, put these 2 in the same thread or put them into the same container. So we refer to that as compute locality. There are these different options in Apex: thread local, container local, node local, rack local, and you can basically set this and control how things are deployed into containers. There's also, in the last release, new generalized support for anti-affinity, where I can say logical operator 1 and 2 should never be on the same machine, or should be on the same machine, because I want to use some shared cache or something else. So those are optimizations for higher throughput, higher performance. So now this is the DataTorrent part. Whatever I said till here is all open source Apex. DataTorrent has value-added proprietary tools. On top of Apex, it also has its own distribution. It is called DataTorrent RTS that bundles those tools. There is a community edition which is free for use, and there is an enterprise edition which requires a license. It's a subscription model to run. So there are some tools that are part of the community edition, like the management console. There are some other things that are only part of enterprise, and there are functions like a role-based access control in the dashboard that is also part of enterprise edition. But these tools are essentially what you probably would like to have to run something in production. You probably don't care when you develop, you just use the CLI, you build an application package, you launch it on the cluster, you don't need those things. But when it comes to production and the ability to have visibility for monitoring, for troubleshooting, then those tools are really helpful. So they are value add by DataTorrent on top of what is provided by Apex. So here's an example. This is a snapshot or a screenshot from the management console. So you can see an application as it runs. It will show the physical plan in this case. It will show some data on how many windows have been processed, what is the latency right now in this entire DAG, and how many events have been processed. It also gives you events about visibility, have there been any failures or any other events that are good to know about. It also gives you the ability to directly navigate to the logs from here. So a lot of data that you might be interested in. Now this data is also available through the REST API, so nobody has to use the UI, but it's of course a much more convenient way than writing scripts to extract data from the REST API. So here we have on the right side is actually this was the logical plan, and here you see the partitions expanded, right? You see that there are multiple block readers for this logical operator. So this reflects the partitioning, the physical plan. So different views for different aspects. And then this here is the dashboard. So I said at the beginning that you can actually take the data as it's being computed in memory, and you can show it directly in a UI. So this is the dashboard component that lets you do that. It can tap into the data that are in memory in the stateful system, so they won't be lost. We can tap into it and do visualizations. There are some pre-built widgets that let you do things like this here, and it's a nice way of doing a quick data visualization. It can also be used for not just for user data, like in this case. It can also be used for metrics that custom operators compute. They can actually be visualized in a similar way without writing any code for it. And then the last part, I want to just mention 3 different use cases. So just to check, are there any questions here? Too much detail, too little? Okay. This is a very good question. This is actually very important when it comes to build a real production-ready application, right? Because you need to tune it. You need to find out what are your bottlenecks, and so right now there is some tooling in this console that I showed you that helps you find certain things. For example, you can, based on the throughput and the latency, you can already see that something is falling behind, right? It cannot keep up. Other things are harder to find. For example, if the memory that you configured is too little, then an operator is a JVM, it can run out of memory and you get an out of memory error. The container fails. You would see the container failure there. What we are actually planning to do is for the most common things that we see people doing over and over again when they tune the application, we are planning to detect those things automatically and then give hints. Well, this looks like you don't have enough memory. This looks like you have too many, you're chewing up too many resources or CPU on one machine, and so that this tuning process is easier. It's not easy to automatically tune this, but certainly it's possible to provide a whole lot of help to less experienced users. Yes. Well, once you have computed the state, it's kind of frozen and final, right? So what you would have to do is you would have to yourself rewrite the state, in that case, to reflect your new windowing semantics if you wanted to do that. Sometimes that may be easy, depending on how you want to change the aggregation. Sometimes it may be really hard and involve a lot of state that you have to load in and write back. So this could be terabytes, right, of data, and if you have accumulated a large amount of history. So it depends on your application. So changing the window at runtime right now, that is not possible. The window is something that you set at the beginning, and that's one of the things that you cannot change dynamically. What you can do with the windowing support that we are adding, though, is to have custom window that takes into consideration such criteria where you may want to change something based on a property. Yes, that could be done, but it would have to be written by the user, the code for it. Ah, okay. Well, that's a different thing. I don't think I have a slide that shows bar charts and things, but typically you have a choice, right? You have the aggregation intervals. You choose time units. I want to see by minute, by hour, and things like that. So is your question, okay, instead of that, I want to see 5 minutes intervals. That, because that can be done. That's something that is evaluated at the time of reporting. So if the time buckets that are being computed are smaller, and then what you want to report on are multiple of those, that can be done on the fly. Yeah, yeah. Yeah, that's a nice question too. So machine learning in a streaming system. So generally, we don't implement the machine learning algorithms. We would like to use the machine learning algorithms that are already out there and apply it to use Apex as the execution engine. So we have this ability to build a feedback loop, right, where a computed result can be fed back as an input, so iteration, which is key to many machine learning algorithms. So it can be done from an engine level, very low level, to use it as an execution layer. Then we are working on supporting things like Samoa, where we would like to take algorithms that are already written and run them on Apex. Currently, the streaming machine learning algorithms, there aren't that many out there. I think that's still an area where we will see more support in the future. So generally, our idea is that we would like to take the algorithms that are already there and run them on Apex. Well, it's a JVM. You can use a different JVM language. You could write in Scala. You could write in I think Ruby, right? And maybe Jython. The comment I have on that is that Java is the prevailing skill set for building production-ready applications. There's an entire separate space that is like exploration and like ad hoc, quick and dirty, putting something together quick. Tools that data scientists use. This hasn't been our focus traditionally. We really want to focus on production pipelines. And then Java is actually a good choice when you look at the overall pros and cons, the skill set that is available in the market, the fact that you can implement a robust system. So Java is a good choice. Even when you look at Scala, Scala really, there's a lot of adoption in certain areas, including the Silicon Valley. But when you go into other areas, there aren't many Scala developers out there. So you look at what enterprises have, what skill set can they hire. Python is a possibility, yes. Yes. Apache Flink, so that's a nice question. So Apache Flink is, so let's first say that Apex and Flink have different roots. The first time I heard about Flink was last year at the Hadoop Summit in Brussels. They come from Stratosphere. The company is in Berlin. It's called Data Artisans. They have built a very fine product. The architecture is actually very similar to Apex, which is a good validation because key aspects like stateful processing, windowing, checkpointing, you will find many of those things repeated. So Apex has seen more production usage at this point in time because we had production deployments, I would say, since early 2014, also at some very large companies. Not all of which I can disclose here, but there are a couple of use cases that I have here on the deck. So there's probably a little bit more maturity. I would say yes? Yeah, maybe. So yes. So if you want to iron out those things, you actually have to run the system in production, and this is how you find those things will mature. So I would say Flink is a very good architecture, and it's probably Apex and Flink are probably the best streaming systems out there. Apache Spark became successful as a replacement for MapReduce, right? So MapReduce was there And then Spark came out and really took over because they could process the same workloads so much faster because of the in-memory data. Right, but it's still a batch architecture. When you look at the stack, you have the underlying engine, which is a batch architecture. You schedule every task. Yes, you can make the intervals very small, but you still keep on scheduling. This works for batch processing. It probably works for SQL because you schedule once. But as soon as you have a situation where you have to schedule every few seconds and then swap the state in and out, this doesn't work very well anymore. And that's why it's not a good fit for stream processing. Very micro batches. They call it micro batches, yes. Yes, so you can, through the REST API, I don't have an example here, you can look at the physical plan. So all the data that you see here is exposed through the REST API, and then some more that is not shown here. So you will see for each operator all the partitions that are there, and also all the properties that are applied to partitions. So yes, you can look inside the system. That's a key operability concern, that you can see what is happening, that is not a black box. You can get the data. You can do it by inspecting from the command line with the CLI. You can do it here. You can also write your own monitoring tool that uses the REST API to pull those things out and maybe passes it on to a different system. Yes. It's a good question. It's a unconventional suggestion, right? To do it this way. Of course, the traditional processing is you compute your data, you store it in a database, then you have other systems that take it from there. Now, this is not going to go away. I don't mean to suggest that. What I'm saying is you can access the state from the in-memory representation directly without relying on those mechanisms. You get lower, so I think the first and obvious thing is that you get a lower latency because the data is already there. You just have to take it from the memory. Yes. Now, even the stream processor needs an efficient way to manage the state. So let's say you accumulate a lot of state, which is queryable. You still have to store it somewhere. It's just not a centralized system that gets hammered from many different partitions. It's like, it can be an embedded store that is exclusive to the partition and owned by the partition. So you get an efficiency benefit there. The data, the query can find its way to the data because you have already partitioned the stream. So if you imagine that your query goes the same paths as the data went originally to the processor, then you have built that already. You don't have to build anything extra to talk to an outside system and have all the concurrency and concurrency issues. For example, when you benchmark this, you will find out that a Redis server will probably top out at around 40,000 writes per second. A stream processor won't, because it has already done that processing in memory. So you get a benefit, but I see your point too. You wanna have the data also stored somewhere for different access. Well, I don't know what he exactly said there, but so let's say Apex. We are storing state in HDFS. When you store state in HDFS, you have replication through HDFS, right? So yes, and you have I/O too. But you have much better control over when you actually want to write out something. you can control that write path to HDFS because it's not necessary to flush it out in order to visualize the data. The situation that you have with the database, you first have to actually write it into the database before you can take the data out there. Yes. Yes. This is a function of the throughput of the system too. Yes. Well, there isn't really a reason not to use it because the community edition is for free, is available for free. So why not use it if it's there? But you can run the system without the management console, just with the command line interface. You can do all the same things through there as well. Yeah. So now I have a few slides in here about use cases. Those are actually customers that have talked about what they implemented with DataTorrent for their businesses. I'm not going to go in through all of the details here because there are separate talks that are actually recorded. There are videos out there and slide shares, and I give the pointers in this deck later. So if you are interested in any of those, you can go and dig into the details. The first one is AdTech, PubMatic. They capture all the logs on their ad servers, and they want to do a dimensional compute on that data to gain visibility into campaign performance. So what that involves is, so I think the peak throughput is around 200,000 events per second. This is actually geographically distributed because ad servers in different regions of the world. They are also in different data centers of the world, and then they bring the data into a hub using Kafka. And in that hub, the processing with Apex happens. This application is an example of what we just discussed. The state being computed in memory and served to a dashboard to the user. Likewise through Kafka, actually. The queries, the interactive queries from the user by looking at the dashboard, they go through a Kafka topic. The results go back through the Kafka topic into the dashboard using a front-end server that they have written. So they have cut down there. This is not exactly a use case of extremely low latency. This is a question of efficiency where they have cut the wait time of several hours down, and they can do the processing with much lesser hardware and with less delay. So real-time reporting using the data visualization, but also dynamic scalability, and they use many of the operators that are part of the Apex library. And then General Electrics, they are using Apex to capture machine data from sensors, bring them into a central hub, again perform dimensional compute on it, cleans the data also, make them available to downstream pipelines. They are building something that's called Predix, which is actually a system that their customers will access to manage their machines and hardware. So, and then the third one, so this is an IoT use case. And then the third one is energy. Silver Spring Networks, they collect the data from their meters, smart meters, and they bring it in for processing. They use Apex to ingest the data, prepare it for storage, and then write it into, so this is the opposite example, right? They write it into tables, and then they use Impala for reporting on it. So this is the example where you actually throw it into a storage backend, and then use the existing SQL query capability to pull it out from there. There's more information here. The links are here. There are also links over here, where are the mailing list, community information, and then past presentations and SlideShare, and also example code. So with that, I would like to open it for more questions, if there are any. No? I mean, one said that Flink is something like the beta max of the like the stream processing engines, because they said that like Spike streaming is so big already that it may already be too late for Flink. So what about Apex? Yeah, it's a similar situation, right? Apex came even out to the open source domain after Flink. Now we open sourced it because we want more adoption. It's not that we have production customers and some large ones too, but we want more adoption, right? More critical mass. So it is true that the question can be asked. Well, it's pretty late, but at the same time, looking at the shortcomings of Spark streaming and looking at the number of use cases that has not even been discovered by users today, because a lot of users, they are just starting to adopt Hadoop. Maybe playing around with still MapReduce or batch processing. So when they come to build, in my opinion, to build production critical applications, then they will pay attention to those things that we talked about because they are necessary to implement them. And I think there's a big opportunity for Flink and for Apex also. Yeah.
So, like for example, Kafka or Confluent is moving towards building ingestion APIs and stream processing and schema repositories and all kinds of stuff. So everybody's starting to move out and build stuff around it.
Yes.
What's Apex doing in this space?
So streaming is the new kid on the block, right? Every few months you see a new framework or some new announcements. So Confluent is slightly different perspective. So they are the Kafka company. And the way I look at it, they're building out things around Kafka. So I say, if you're using Kafka, then why also don't you use Kafka Connect? Why don't you use Kafka Streams? And you can do your processing with it. I think Kafka Streams is not a framework, right? Kafka Streams right now is just a library. You have to do a lot of things still to make that implement your use case and make it even viable production use case. So let's wait and see how the adoption is. I don't know where they want to go with it, whether they want to expand and build another Flink or another Apex, or whether their goal is really to make people use Kafka. Because if you position the case like this, well, you can do everything you need as long as you have Kafka, and then if you want to bring your data in, well, then just use Kafka Connect, put it into Kafka. If you want to compute something, use Kafka Streams. I could turn it around, right? And I could say, well, if I have the data already in files, then why do I need Kafka? You can build your ingestion application with Apex that reads the files directly. You can read from a database directly. So I think if the infrastructure is already Kafka, then probably that's a very good fit. If nothing is there right now, then I would argue that the stream processing frameworks deserve a look.
Is there anybody doing stream processing without Kafka?
Is there any stream processing without Kafka? Well, yes. I mean, there are other.
Do you have actually live?
Yes. I mean, for example, the PubMatic use case before they use Kafka, they use file ingestion. GE is using file ingestion because think about it. The data is why? Why? Because the data is accumulated offline sometimes, and then it's uploaded as a batch. So the ingestion mechanism is sometimes not streaming oriented, even when you process it streaming oriented.
Everything is streaming oriented. I mean, even if you're batching something locally in like an IoT device, yes. As soon as you can send it, that's an event.
Yes, that's an event or a stream of events, right? A log file can be seen as a stream of events too. That's correct. But you can just Kafka is a remote access to a log file. So what if I read the log file directly? I get the same thing, right? I just don't go through the Kafka broker. Right? My file could live in HDFS and I can read it from there. Now, I'm not saying we shouldn't use Kafka, but it's not the only source of data for streaming applications. And then there are still some other messaging systems, right? There will be systems out there that use Solace maybe, and MapR has done a different implementation for Kafka. So I think the world is probably a bit more colorful than just Confluent.
Since you mentioned that you just open sourced it some time ago, how is the adoption, or what's your perception about it?
Yeah.
Because
Yeah.
you mentioned lots of companies which adopt the product, which is great for you because it creates money, right? But how's the perception from the community?
I think it's probably too soon to say. Based on the current trends, what we are looking at several metrics. We are looking at outside contributors. We are looking at the meetup communities. We are looking at interest on user mailing lists for people that actually try to implement things with Apex. So we have seen the uptick, especially since it became a top-level project. We have also seen interest at conferences about the topic, but I think has been just a few months, right? So we need to wait a little bit longer to have more data on that. But in general, my opinion is the space is very large. I don't see a scenario where there's just one player doing everything. Any more questions? Good. I will be around after the talk, even if you want to ask more questions. So I'm here. Thank you.